everyone. Welcome to all of you in the lecture series of the course of Novel Technology in Food Processing and Preservation. I am Ajit Singh, Assistant Professor of Food Technology Department at Harcourt Butler Technical University, Kanpur. As discussed earlier, the course Novel Technology in Food Processing and Preservation is very useful for the students, research scholars, and faculty interested in the detailed study of the advanced techniques of food processing and preservation. Today we will discuss about the membrane separation technology as mentioned in module 1 of the given syllabus. So for the past few years, the use of membrane technology as a handling and separation method in food processing is gaining wide application. Membrane separation can be used either as substitute to conventional techniques, especially in dairy, sugar, fruit juice processing, and beverage industries. Membrane separation are considered green technology because of its easy handling and processing nature. In many cases, membrane processes are more advantageous than traditional technology. For example, using cold pasteurization and sterilization with suitable membranes instead of high temperature treatment for the removal of microorganisms is more economical in terms of energy consumption, quality of products, minimize loss of nutritional value. Using membrane filtration to remove microorganisms for shelf-life extension of foods instead of using additives and preservation also creates a green image for the processed food as well as for the processing procedure. In this lecture, we will discuss about the fundamental knowledge of membrane separation technology. Here, as membrane separation is defined essentially as barrier which separates two phase and restricts transport of various molecules in a selective manner. Membrane processing is a technique that permits concentration and separation without the use of heat. Particles are separated on the basis of the molecular size and shape with the use of pressure and especially designed semi-permeable membrane. There are some fairly newly development in terms of commercial reality and it's gaining readily in application. For example, proteins can be separated in whey for the production of whey protein concentrate. Milk can be concentrated prior to cheese making at the farm level. Apple juice and wine can be clarified using membrane technology. Waste treatment and product recovery is possible, especially in edible oil, fat processing, potato processing, and fish processing. Fermentation broths can be clarified and separated with the help of membrane technology. Whole egg and egg white ultrafiltration as a pre-concentration prior to spray drying is used in Western countries. So there are widespread application of membrane processing, and because of its novelty, the use of membrane separation has been increasing exponentially in food processing. Further, membrane processing works under membrane separation and according to the driving forces of operation. It is possible to distinguish by means of pressure, concentration, temperature, as well as electrical potential gradient. Pressure driven operations are microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. Example under concentration driven operation is forward osmosis. Apart from this, other concentration driven operation can be exemplified as gas separation, dialysis, and pervaporation. Again, membrane distillation is a temperature driven separation process in which separation is driven by phase change, and in last, operation in an electrical potential gradient can be termed as electrolysis. Today, the most important use of conventional Electrodialysis is the desalination of brackish water for the production of potable water. However, other applications are gaining increasing importance, including large-scale industrial installations in the food industry, whey and molasses demineralization, tartaric stabilization of wine, and de-acidification of fruit juices. But in this lecture, we will discuss about pressure-driven process only, especially focused on microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. Membranes, which is an integral part of membrane separation technology, can be defined specifically as an interface that separates the two phases and restricts the transport of various chemical species through it. Membrane can be thick or thin, symmetric or asymmetric, natural or synthetic, homogeneous or heterogeneous. The selection of membranes as an effective barrier is very crucial in the application of membrane technology in food processing. Membrane technology can be applied to several production methods, including milk solid separation in the dairy industry, juice clarification and concentration, concentration of whey protein, sugar and water purification, and as well as food waste management. Knowledge of various membrane technology and how they are used in the food industry can be enhanced overall production and offer cost-cutting operation for a variety of separation. Membrane process covers a group of separation process in which the characteristics of a membrane, that is porosity, selectivity, elective charge, are used to separate the components of a solution or a suspension. In this process, the feed stream is separated into two: the fraction that permeates through the membrane, called the permeate, and the fraction containing the component that have not been transported through the membrane, usually called the retentate or concentrate. The size of the component to be separated and the nature of and magnitude of the driving force provide criteria for classification of the membrane separation process. In general, either the concentrate or permeate stream is the product of our interest during separation process, where driving forces may be either pressure, temperature, electrical potential, and concentration. For example, in case of reverse osmosis, for purification of water, permeate is pure water, whereas milk protein is as retentant or concentrate in case of separation of milk protein using ultrafiltration. Membrane separation process have a very important role in the separation industry. Nevertheless, they were not considered technically important until the mid-1970s. Membrane separation process differ based on separation mechanism and size of the separated particles. The widely used membrane process driven by pressure include microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. Components smaller than membrane pore size pass through the members, while large components are retained. Components can be selectively separated over a wide range of particle size. Membrane process separates molecules on the basis of size and molecular weight. In the process of membrane separation under the head of microfiltration and ultrafiltration, particle size is practically the sole criteria for permeation or rejection, whereas nanofiltration and reverse osmosis separates particles at molecular level and their selectivity is based on the chemical nature of the species or particle. The use of membrane filtration in food and beverage processing offers a wide range of advantages for the consumers as well as processor. On the one hand, filtration technology offers an efficient way to gain superior quality and safe without destroying the fundamental sensory qualities of the food product. It removes unwanted ingredients like microorganisms, drugs, or sediments that have a negative impact on product quality, making the final product more attractive in texture and increasing the shelf life. On the other hand, it may reduce some production steps and increase yield that has a higher degree of selectivity and improves control over the production and process and has low energy cost. The development of filtration technique and their distribution is not yet complete. It has been found that there is a continuing development of new applications based on the membrane techniques. Microfiltration. Microfiltration usually serves as a pre-treatment for other separation process such as ultrafiltration and a post-treatment for granular media filtration. The typical particle size used for microfiltration ranges from about 0.1 to 10 micrometers and operating pressure is around 1 bar. In terms of approx molecular weight, these membranes can separate macromolecules of molecular weights generally less than 100,000 gram per mole. The filters used in the microfiltration process are especially designed to separate starch, bacteria, fat, molds, yeast, and emulsified oils. Microfiltration or MF offers unlimited new process opportunities in the membrane market, especially as pre-treatment process. Microfiltration provides a low temperature processing alternative to thermal methods like ultrapasteurization for reducing the number of bacteria in fluid milk or in whey as well as fruit juices. Microfiltration is used in dairy industry for marketing low heat sterile milk. Further, microfiltration membranes can be used to remove bacteria and fat and produce protein isolates and concentrate without affecting the functional protein properties of proteins due to low applied temperature. So another membrane filtration that we are going to discuss is ultrafiltration. Ultrafiltration is a membrane separation process similar to microfiltration but with even smaller membrane pore size, allowing particles in the range of 0.01 to 0.1 micrometers. The pressure used is generally higher than microfiltration process and in the range of 1 to 10 bar. Ultrafiltration separates colloidal material, emulsified oil, and large organic molecules using suction or pressure by means of colloidal filter. Ultrafiltration has larger pores than nanofiltration and reverse osmosis and is therefore the least costly of the three to operate. Ultrafiltration has less porosity than macrofiltration and high porosity than RO. So if we discuss about the application of ultrafiltration, with the development of improved membranes, ultrafiltration has become a major separation process, especially in food and dairy industry. The two largest area of application are the pre-concentration of milk for cheese manufacture and the production of protein concentrates from whey. Both applications are related to cheese making. Other applications include use to separate milk proteins by passing milk at a very high pressure through very fine membrane. Pre-treatment to other organic systems like ion exchange where organics are not removed. Also, gelatin and protein concentration in nutraceutical industry or pharmaceutical industry. Further, sugar clarification and in cheese whey concentration, ultrafiltration is being utilized for separation process. Fine-tuned to selectivity, remove proteins or sugar. Concentrate skim milks for ice cream. Color removal for beet molasses by ultrafiltration. Other application include color removal for different food products and reverse osmosis process, where it is used as a pre-treatment. Ultrafiltration is used as a pre-treatment to prevent falling by suspended organic material and colloidal materials. So there are ample examples where ultrafiltration is used in food processing as well as in preservation or as well as in food waste management. So another membrane separation process is nanofiltration. Nanofiltration is a pressure-driven membrane operation with separation process or separation characteristics between those of reverse osmosis and ultrafiltration, and widely used for several applications including food processing operation. With the increased demand for products with greater nutritional value and environmental friendly processing as well as procedure, nanofiltration has become a reliable and techno-economically attractive operation in the food processing for the fractionation, concentration and purification of different products and byproducts. Nanofiltration separates food components in a region between reverse osmosis and ultrafiltration. As said earlier, the typical particle size used for microfiltration is about 0.001 to 0.001 micrometer, and operating pressure is in the range of 20 to 30 bar. Separation by nanofiltration is affected generally by the charge. Nanofiltration allows monovalent ions while rejecting high percentage of divalent cations and multivalent cations. This is the exact property for which we are using nanofiltration, especially in food processing industry. Further, nanofiltration is also becoming more widely used in food processing applications such as dairy for simultaneous concentration and partial, that is monovalent ion demineralization. In demineralization process, nanofiltration works efficiently in comparison to other three membrane separation process. Further, nanofiltration application includes as sugar concentration, dye desalting, color removal in water, antioxidant properties of tofu whey concentrate by freeze concentration and nanofiltration process. Other application that include partial demineralization of whey, pigment concentration, especially in anthocyanin concentration, molasses purification for reuse, oil degumming and refining in oil processing industry, removal of heavy metals and arsenic, and as well as in water softening in water processing industry. So nanofiltration having a particular applicability range which works on the pore size 0.001 to 0.01 micrometers have a very efficient role as a membrane separation process. Here we are going to discuss about the reverse osmosis. Reverse osmosis is the major separation process categorized under the pressure driven membrane separation process. You might have heard about the osmosis. Osmosis is simply diffusion driven motion of water through a membrane. In osmosis, water molecules move across a semi-permeable membrane from a higher concentration liquid to lower that requires no extra energy expenditure nor any external process. In RO, if we consider especially about the water molecules move across a semi-permeable membrane from a lower concentration liquid to a higher one, which is the reversal of regular osmosis. This requires pressure to be applied in the lower concentration liquid in order to overcome the osmotic pressure and thus extra energy. Here it has been depicted in the diagram. Higher is the pressure, higher is the driving force. Further, higher pressure are necessary to overcome osmotic pressure. We will discuss in the engineering part about the how much pressure is required for different food products like juice, uh, then other fruit juices from different fruits to overcome osmotic pressure. So basically reverse osmosis is the most complex techniques in membrane separation. Although reverse osmosis is recognized as a leading technology in desalination process, it is also a well-established application in food processing due to several advantages over conventional methodologies such as the preservation of thermal sensitivity compounds, low energy consumption, and low investment cost. Reverse osmosis operates with high compact membrane pore size, allowing particles lesser than of 0.001 micrometers to pass through. High pressure of about 30 to 60 bar are required in order to overcome the high osmotic pressure across the membrane. In reverse osmosis, charge of particle facilitate separation. Larger the charge and the particle, more likely it will be rejected. Application of reverse osmosis includes to reduce inorganic salt in water. Other applications include to remove bacteria, salt, sugar, protein particles, dyes, water recycling, concentration, milk solids, and removing water from whey. In the upcoming lectures, we will discuss in detail about the reverse osmosis and their applications in food processing industry for different processing of food products in detail. Membrane process covers a group of separation process in which the characteristics of a membrane that on the basis of porosity, selectivity, electric charge are used to separate the components of a solution or a suspension. The different membrane processing methods, that is microfiltration, ultrafiltration, nanofiltration, and reverse osmosis, are compared here and depicted in figure to recognize the differences early. Here in the diagram of the comparison, these are categorized on the basis of pressure bars and operating pores. Reverse osmosis has the tightest pore concentration and can separate in the ionic range. Nanofiltration is a newer category of membrane, operates similar to reverse osmosis but has a somewhat looser construction, allowing monovalent ions and some divalent ion to pass. Ultrafiltration is used to separate different size molecules such as proteins and other macromolecules. Macrofiltration, we have already discussed, is a membrane have the largest pore size of all categories and is primarily used for removing suspended solids and bacteria, and most of the time it is used as a pre-treatment. So this was the fundamental concept of a membrane technology, where we discussed about the membrane separation, especially by pressure driven operation. In the food and beverage industry, membrane filtration is a state of the art technology for clarification, concentration, fractionation, that means separation of components, desalting, and purification of variety of beverages. It is also applied to improve the food safety of products while avoiding heat treatments. In the next lecture, that is lecture 3, we will discuss about the type of process of membrane filtration, membrane modules like flat, shear membranes, spiral wound, tubular and hollow fiber membrane module, and membrane material in detail. In case you want to have any question, you may ask by putting your question in comment section or send to referred in email directly. That is all for the lecture 2 we have discussed in membrane separation. In case Again, if you have any questions, you may ask by putting your question in comment section or send to referred email directly. Have a good day. Thank you.